Well, what do we have here? The return of fish fry. Hey, everybody! Welcome to episode number 460 of this here electronic engineering podcast called Amelia's Weekly Fish Fry. Brought to you by eejournal.com and written, hosted, and produced by yours truly, Amelia Dalton. Yes, I took a little hiatus last week because of the Thanksgiving holiday, but this week we're back, and we're talking about the world of 3D ICs, self-reproducing xenobots, and more. So, in other words, we better get started. First up, a little news you may have missed. Self-reproducing xenobots edition. So, did you hear that a team of researchers at the University of Vermont have created the world's first self-replicating living robots? Maybe you have, because this story is everywhere. It even made its way all the way to CNN this week. But here on Fish Fry, we've been talking about these living robots since January. Okay, so what are we really talking about here? A team of researchers at the University of Vermont in January of 2021 created millimeter-sized living programmable organisms. With the help from some programmed, repurposed living cells scraped from frog embryos, and the help from a specialized algorithm that created thousands of simulated designs for new life forms. And bam! A new class of artifact called xenobots was born. Now, fast forward to this month, December 2021, these xenobots can now replicate themselves. Skynet, here we come. So it's not just that these xenobots can now reproduce by themselves. That's the most important part here. This team from the University of Vermont, along with researchers from Tufts University and the Wyss Institute for Biologically Inspired Engineering at Harvard University, have actually discovered an entirely new form of biological reproduction. Douglas Blackston, Ph.D., the senior scientist at Tufts University and the Wyss Institute, who assembled the xenobot parents and developed the biological portion of this new study, says this about the importance of this new study. People have thought for quite a long time that we've worked out all the ways that life can reproduce or replicate. This is something that's never been observed before. So, how does this new form of reproduction apply to these new millimeter-sized living programmable organisms? Well, these researchers found that their xenobots can actually swim out into their petri dish, find single cells, gather hundreds of them together, and then assemble these baby xenobots into their mouths. And then, bam, a few days later, look at that. There are new xenobots that look and move just like their parents. In earlier experiments, like we reported on in January of 2021, the scientists involved in this research were amazed that these xenobots could be designed to achieve simple tasks. But this new research was beyond what they had even considered possible. That a computer-designed collection of cells can and will spontaneously replicate. Michael Levin, Ph.D., a professor of biology and director of the Allen Discovery Center at Tufts University and co-leader of this new research, puts it in focus like this. This is profound. These cells have a genome of a frog, but freed from becoming tadpoles, they use their collective intelligence and plasticity to do something astounding. Just like the creation of these xenobots last year, an important key in this new discovery is the use of an artificial intelligence program that uses the Deep Green supercomputer cluster at UVM's Vermont Advanced Computing Core. This algorithm was able to test billions of body shapes in simulation. Pyramids, triangles, starfish, squares, with the goal to find a body shape for these parent xenobots that would be the most effective at a motion-based kinematic replication. And eventually it came up with the shape of a Pac-Man. And guess what? It worked. Now, this kind of kinematic replication is not new. It's a well-known way to reproduce molecules, but had not been observed at this scale ever before. Sam Kriegman, PhD, the lead author of this study, explains the role of the deep green algorithm further like this. He says, "We asked the supercomputer at UVM to figure out how to adjust the shape of the initial parents. And the AI came up with some strange designs after months of chugging away, including one that resembled Pac-Man. It's not very intuitive, but it looks very simple, and it's not something that a human engineer would come up with. Why one tiny mouth? Why not 5? We sent the results to Doug, and he built these Pac-Man-shaped parent xenobots. Then the parents built the children, who built the grandchildren, who built the great-grandchildren, who built the great-great-grandchildren." So, where are we going with this research? Well, everywhere. To new avenues for medicine and beyond. Joshua Baumgard, PhD, a computer scientist and robotics expert at the University of Vermont who co-led this research, says this: "We are looking to understand this property, replication. The world and technologies are rapidly changing. It's important for society as a whole that we study and understand how this works. This is an ideal system in which to study self-replicating systems. We have a moral imperative to understand the conditions under which we can control it, direct it, douse it, and exaggerate it." Baumgard goes on to explain that this type of research goes way beyond building xenobots and petri dishes. He says, "The speed at which we can produce solutions matters deeply. If we can develop technologies, including xenobots, where we can quickly tell the AI, we need a biological tool that does X and Y and suppresses Z, that would be very beneficial. We need to create technological solutions that grow at the same rate as the challenges we face." Wow. So maybe not Skynet just yet, but maybe these little Pac-Man xenobots will be able to teach us more than we ever expected. If you want even more information about these self-replicating xenobots, I've included a couple links below the player on this week's Fish Fryin' page on eejournal.com, including the research paper published by this team and a video of them in action. Super cool. All right, it's time for something completely different: the rise of 3D ICs. Please welcome Vinay Patwardhan from Cadence Design Systems. Vinay and I are chatting about the challenges engineers experience when designing 3D chips, where existing 3D IC tools or methodologies fall short, and what type of analysis is needed for a 3D stacked system as opposed to a standard chip design. Hi, Vinay. Thank you so much for joining me.
Hi, Amelia. Thank you for having me.
Absolutely. So we're talking about 3D ICs today, but Vinay, why do you think 3D ICs are trending these days?
That's something interesting that has been going on since the last year or so. 3D IC has been around for some time. We've had our customers and some of the top chip makers experiment around with this technology for some time, but in the last couple of years, it has really picked up and, as you said, starting to trend. And I think there are a couple of reasons for that. On the large data centers, there is this whole data cycle where everyone is acquiring a lot of data, processing it. So the hardware that's being used currently in the large data centers or these hyperscalers is not very well suited to handle this large amount of data. I mean, they can handle the data, but then the power consumed is very high. So they are trying to look at new architectures that will be more efficient for moving data around, processing the data. And for that, they're going to advanced nodes as in like 7 nanometer designs, 5 nanometer designs, 3 nanometer design. But now we are actually reaching the physical limits of a transistor, the basic element in a chip. We don't know what's after that, what's after three. How do you continue the scaling of the famous Moore's law? So that's one thing. Another thing is some of these, again, data type applications have a certain requirement of having lots of processing elements on a single die. And because of that, the size of each die is so big that now it's reaching the reticle limit. By that, what I mean is today's lithography machines have a physical limit of how big a die they can manufacture, which is 853 millimeters square. So some of these dies for these high-end GPUs, high-end CPUs are in the range of 700, 800 millimeters square. And you can't make a chip bigger than that, even if you want to process more data or add more memory. There is a physical limitation again on that. So that's why an easy solution to that is start stacking chips on top of each other. They may be smaller, but two chips stacked on the same package can be an elegant solution for what I just described, where we need some new architectures with a lot of on-chip memory on the same package. So that's why I think in the last year or so, or more, year and a half, 3DIC has really gained popularity and it's quote unquote trending.
So, Vinay, what are some of the difficulties engineers experience when designing 3D chips? And where do existing 3D IC tools or methodologies fall short?
So, as I mentioned, 3D IC as an idea, as a concept, and even working silicon has been around for some time. But the way it's done today is each of these designs that is either stacked on top of each other or put close to each other, connected by an RDL interposer or a silicon interposer. Each of them is done individually, separately. The packaging teamwork and the SoC design is also done separately. At some point, they start exchanging data and they realize, oh, a lot of things that we didn't anticipate from the package side, we have to redo in the SoC. And similarly, package designers also have to keep rebuilding the package. Or when you're stacking two chips, you have to exchange the abstracts of each of the chip. It's more like a lightweight model that has to be placed on top of the chip to design that chip, taking into consideration where the connection points between the two are. So you're practically doing like a stacking of Lego blocks, but you have to be aware of where the bumps are and how they will fit right on top of each other. Now, if you're doing this separately in silos, aligning that takes a lot of time, a lot of iterations. That's one really big challenge, that how do you do all of these multiple chips in one single environment? The construction cannot be just based on the geometries and the location. The connectors between these 3D chips have electrical properties, so they have to be analyzed in details at the system level. Each SoC at its own level can be closed, physically verified. But when you start stacking them, you have to do a lot of system analysis. There will be switching things on each of these dies, resulting in power dissipation and rise in temperature. So all that has to be analyzed correctly. There would be inter-die connectivity that has to be traced correctly. So all of this has to be done in one single way, and that feedback has to be provided to the construction step when you're constructing this whole system. And that is what I think is lacking today in some of the methodologies and causing it to be a really challenging task, much more than designing a standard 2D SoC.
Now, there is also the issue of too many components in a system, right? How do you think we should all bring them together?
When we talk about 3D IC, we are talking about a whole system. And the system has multiple parts. It has the package on which the connecting layers sit. It has something like the interposer, and they can be RDL interposer or silicon interposers. It has an analog IC. It has a digital component. It may have some special IP, really high speed in a totally different node. So it has a bunch of components. They all need to be represented in such a way that all of this information is available together in one place. There is some innovation needed in there where, although something is at a really old technology node, 130 nanometer or something, and some component of the system is at 5 nanometer, the most recent node. And what we really need is a single database which can bring all these pieces together and represent them in a hierarchical way. So it's very clear to the system designer what each view of that component is. It should have multiple levels of abstraction. It should have a unification of all the data and flexibility to represent multiple components from the system in different formats. That's what is really needed to make it easier.
Now, what type of analysis is needed in a 3D stack system as opposed to a standard chip? And how do you incorporate all of that while doing a 3D IC design?
When we do a standard 2D design, our customers have been doing it for many years now. So there is standard timing analysis, there is standard EMIR analysis, power analysis, LVS and DRC, physical verification checks that we do at the end of the design cycle to make sure that the design is functional and robust. Now, when we are talking about 3D system, there's additional checks that need to be performed. Since now we have a stack of dies on top of each other, and both of them have millions of transistors on them, there is going to be switching happening at the same time. Because of that, there's going to be power dissipation, and power leads to a rise in temperature. So one of the key analysis is temperature analysis that has to happen, thermal analysis. So once the temperature of the system goes up, those increased temperature numbers have to be incorporated back into the standard analyses, and more analysis needs to be done. Sometimes while doing timing analysis, we have these PVT corners. We anticipate there'll be a lot more temperature corners for a 3D IC system. Also, when you have these two dies together, there was a connectivity defined at the beginning of what the two dies would look like. So having an inter-die connectivity check, like an LVS check, but with two dies involved, a layout versus schematic. So netlist connectivity versus what you actually laid out with the two designs. There has to be a smart way to traverse from one die to another die on the connectivity side and make sure it's verified on the layout side as well. Also, there will be additional rules from the foundry. There'll be design rules for the layouts on how far the dies can be next to each other or when they are on top of each other, how much clearances each should have around the elements that are connecting them. So all those will be additional checks that are needed in a 3D IC system. So it is a lot of new things that normally package designers and system designers are used to. But as SoC designers transition into building 3D designs, those additional checks will need to be performed during the design cycle as well.
So, Vinay, I heard you guys just launched the Integrity 3D IC platform. So give me some details about this.
Yes, we did. As I talked about some of the challenges and what's really needed to bring all this together, we at Cadence have been working on addressing some of the challenges through all the technology that's available at Cadence. So at Cadence, we have a digital implementation platform. We have a very strong packaging platform in Allegro, and we have an analog RF design platform with Virtuoso. So with this Integrity 3D IC platform, we are really bringing together the technology for any kind of 3D IC that you're trying to do. It's a platform that can do 3D design, implementation, and all these analyses that we talked about. So it has an analysis flow manager that can call thermal analysis, STA, inter-die DRC, LVS, power analysis, all of that through our individual sign-off tools is available through the platform. So it's really a comprehensive unified platform with a unified database that brings all these pieces together, lets you design 3D ICs of different formats, and lets you analyze very early during your design cycle your stack, your 3D stack or your configuration to see if you're doing the right thing. And it will provide you early feedback from system level analysis that will help you make the right changes needed in terms of changing the configuration or changing actually the contents of the design that will help you improve the power, performance, and area of the chips that are going into this 3D configuration. So that's why we are calling this, what the platform really provides. It's system-driven PPA. From the system side, all the analysis will give you good, solid engineering feedback to improve the designs you're putting in a 3D stack.
All right, Vinay, it is time for your off-the-cuff question. Now, I know you're a big Giants fan. What are your chances to take the whole thing this year?
This regular season was so stressful, and I can't believe that it had to be on the 162nd game that the division winner was decided. So I'm still soaking that in. And while I'm doing that, they're already up 2-1 against the Dodgers. So I am keeping my fingers crossed. I'm cautiously optimistic. There've been a lot of injuries on the team, but man, the Giants are playing so well this year. I love watching them.
That's excellent. It's been a good year for baseball, I must say. Well, Vinay, I think that's all I have time for today. Thank you so much for joining me.
Thank you, Amelia. Thank you so much. This was fun.
And before we go, don't forget to check out my new maker-themed monthly fish fry podcast series called Makers Today. In our 6th episode of this series, I chat with Richard Curtin and Katie Chubb from OKDo. We chat all about OKDo's mission to encourage inspiration with the OKDo Projects Hub, how you can recycle your pre-loved Raspberry Pis with their new OKDo Renew program, and how they are encouraging STEM education throughout the world. You can check out this episode of Makers Today by clicking the link below the player on this week's Fish Fryin' page on eejournal.com. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EEJournal. If you're into Twitter, you can monitor our tweets at EEJournalTFM. And don't forget, if you want to follow my personal Twitter account, check out Amelia D. 1978. And hey, if LinkedIn is more your thing, sure, I dig it. You can follow us or me on LinkedIn as well. And we have a YouTube channel, youtube.com/EEJournal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series hosted by yours truly. And you can subscribe to our EE Journal YouTube channel as well. Also, by clicking the links below the player on this week's Fish Fryin' page, you can subscribe to this here podcast through Spotify, Podbean, or Apple Podcasts. And remember, if you'd like to further support this podcast, please leave me a review on that podcasting platform of your choice. It really does help. Also, if you'd like any further information about the stories covered in today's show, just head on over to eejournal.com and look for this week's Fish Fryin' page. Thank you everyone for tuning in. If you know of any cool new technology or heck you just want to chat, shoot me a line at Amelia, that's AMELIA, at eejournal.com, or post a comment on our forums on EE Journal. For the week of December 3rd, 2021, I'm Amelia Dalton, and you've been fried.